Hello everybody, and welcome to our video on infinite limits and limits at infinity. So now we're going to deal with special cases that are just examining what's happening to functions as they grow in certain ways. So either as the output is growing unbounded, and when I say growing, I mean could be coming larger towards positive values, or the magnitude could be coming larger but towards negative values, or asking what's happening when the input is getting larger, either towards positive values or negative values. So in this case, we're going to start with what we call limits to infinity, or infinite limits. So consider the graph of this function, f of x equals 1 over x. So for example, we know that when I plug in 1, I get 1. When I plug in 2, I get 1/2, 3, I get 1/4, so forth and so on. But if I plug in 1 over 1/2, I get 2, right? So 1 over 1/2 gives me 2, and 1 over 1/4 gives me 4. And in that way, what I see is that this expression grows larger and larger the closer this denominator gets to 0. The smaller the x value gets, the bigger this goes. And similarly, if I'm looking at negative values of x, 1 over negative 1/2, that's negative 2. 1 over negative 1/4, that's negative 4. Right? I'm still getting growth in a sense, but the growth is towards negative values, so the y values become larger in magnitude, but in the negative direction. So when we see this behavior, whereas our input approaches a certain number, the output grows unbounded, that's what we mean when we talk about infinite limits. So when x approaches 0 from the right here, we see that f of x increases without bound, so we notate this as x arrow 0 from the right. So x approaches 0 from the right, f of x approaches infinity, or the limit as x approaches 0 from the right of 1 over x equals infinity. On the other hand, when x approaches from the left, f of x decreases without bound, so we notate this, the limit when x goes to 0 from the left of 1 over x equals negative infinity. Right? So the first case just says, hey, when I'm coming from the right, when I go from the right towards 0, my graph goes up and never stops going up. And when I go from the left towards 0, my graph goes down and never stops going down, right? So in the first case, the limit is called infinity, and in the second case, the limit is called negative infinity. So I want to add a little something here to be clear. These limits don't actually exist. So when we talked about limits in the previous section, we talked about the fact that if our numerator approached a non-zero number and our denominator approached 0, we would say that the limit doesn't exist. That's still true, because when we say a limit exists, we mean that it approaches a finite value, it approaches a real number, and infinity is not a real number. This notation is sort of just an abuse of the limit notation to add extra information, right? We're saying, hey, the limit when x goes to 0 from the right of 1 over x, it doesn't exist, but also this function grows unbounded there. And the limit as x approaches 0 from the left of 1 over x doesn't exist, but also this function goes down unbounded there, right? So we're just adding extra information. These are limits that don't exist, but we also know what behavior the function is exhibiting at those places, either growing towards infinity or negative infinity. Okay, so writing this as a definition, we just say if f of x increases unbounded as x goes to c from the right or left, we say that the limit as x goes to c from the right or the left is infinity. If it decreases unbounded as x goes to c from the right or left, we say that the limit as x goes to c from the right or left is negative infinity. So here's another image just to illustrate the idea. Further, I'm looking at this graph and I say, oh, what's happening to the limit as x approaches c? Well, when x approaches c from the left, I trace along the graph, it's going up and it's not going to stop going up. So we say that this limit is infinity. Oh, but when I look at the right side, if I trace towards c from the right, I'm going down. And so what I say is that the limit as x approaches c from the right of the function is negative infinity. So just an extra example to reinforce this idea in terms of how we interpret graphs. All right, so let's do some examples involving this. So we're going to kind of use a little bit of a universal fact here. And so this fact is that if your limit of your numerator goes to a non-zero and your limit of your denominator goes to 0, then you get some sort of infinity for the limit of the rational function. So again, this limit doesn't exist, but it's some type of infinity. If we get a non-zero, a numerator that's approaching a non-zero value, and a denominator that's approaching 0, then we get some type of infinity plus or minus. Now, how do we determine which type of infinity that is? I'm just going to move this a little bit for my sake. How do we determine which type of infinity that is? We look at the signs, meaning the positive or negative values of the factors in the function. So let's take a look at this example. X is approaching 2 from the right. Well, when my numerator, when x is approaching 2 from the right, this is approaching 6. It's approaching 6 from the right, from values bigger than 6, but that doesn't really matter because numbers slightly bigger than 6 are positive, numbers slightly smaller than 6 are still positive, right? When I say slightly, I want you to imagine a number really, really close to 6. Don't be like, yeah, but -1 is left of 6. Well, that's not what we mean. We mean numbers really close to 6. But our denominator is approaching 0, right? 2 minus 2 is 0. But here's the tricky part. Here's where you have to think carefully. If x is approaching 2 from the right, that means values bigger than 2. That's what from the right means. So if I have a number bigger than 2 and I subtract 2, I should have a positive number. So I should be approaching 0 from the right. So now I look, my numerator is approaching 6. My denominator is approaching 0 from positive values. Positive divided by a positive is a positive. So this is positive infinity. Now, one thing I do want to point out, I do not ever want to see anybody write equals 6 over 0 from the right, because you cannot divide by 0. These functions are undefined here. So I don't want to see equality. If you draw a little arrow, it says, hey, arrow, this goes to 6, this goes to 0 from the right, that's fine. But don't say equals something divided by 0. That doesn't really make sense. I considered it a big time abuse of notation. So be careful about that. It can cause some confusion. Okay, so let's take a look at another example. Now we're looking at the limit as x approaches 2 from the left. Well, 3x is still approaching 6, and 6 is a positive number. Now x minus 2 is approaching 0, but this time these are values from the left of 2, so values smaller than 2. And if I take something smaller than 2 and I subtract 2, I get a negative number. So if I get a negative number, I'm approaching 0 from the left. And so now I have a positive divided by a negative. That's a negative number. So this is approaching negative infinity. Right? All we're checking, we check that our numerator gives us something that isn't 0. We check that our denominator gives us 0. And then we go, hey, what are the factors, right? What are the signs? And we know, hey, a positive divided by a positive is positive. Positive divided by a negative is negative, right? Okay, example 3. Now here we've got the limit as x approaches 2 from the left of 3x over x minus 2 squared. So now when I look at 3x, this is approaching 6. Now this denominator is a little trickier because x minus 2 is from the left, it's smaller than 2, minus 2, so this is approaching values of 0 that are negative, but then I'm squaring it. So the whole thing is actually approaching 0 from positive values. So I get a positive divided by a positive, which is a positive, infinity. Okay, and let's look at example 4 here. Now here I've got a polynomial divided by a polynomial, and I notice that in the numerator I'm approaching 5, in the denominator I'm approaching 0. If I plug in 3, I get 0 in the denominator. But it's hard to tell what the sign of the denominator is as is, right? If I say 3 from the right, I get 9 from the right minus 6 from the left because I'm multiplying by negative 2. Minus 3, so which is it, from the right or left? You get conflicting information. So when we ever get a problem like this, if at all possible, we always want to factor any quadratic expression we get so that we can make it easier to work with. And when I factor this, I get factors of negative 3 that add to negative 2. That's minus 3 and plus 1. And now this is going to be a lot easier to figure out because my numerator is just going to approach 5, which is a positive number. Now x plus 1 is simple because, hey, I plug in 3, this is approaching 4, and that's a positive number. Now x minus 3, that's approaching 0. All right, so now we have to be careful. 3 from the right, numbers bigger than 3, minus 3, that's a positive number. So we're approaching 0 from the right. Okay, so now if I have a product of two positive numbers in my denominator, one of which is approaching 0, then this is approaching 0 from the right. So we have a positive divided by positive. That's positive infinity. All right, and that's it for these infinite limits. Now we're going to move on to limits at infinity. So let's take a look here. So here we're talking about end behavior of a function. So what happens when x goes to infinity or negative infinity? In other words, x goes to the right forever, or x goes to the left forever. Okay, so what's happening in this first graph? Well, if I trace along the graph towards the right, what do I see? 1, 2, 3, 4, 5. I see that the y value is approaching 5. What if I draw along the graph towards the left? Well, I see that the y value is approaching what? That should say x approaches negative infinity of f of x. Well, 1, 2, 3. Oh, I'm approaching negative 3. All right. And now let's take a look at this case over here. So when I approach towards the left, we'll do that one first this time. As x goes to negative infinity, my graph is going upwards. So my y value is going up, so I just say the limit of that is infinity. Right? So this limit, the x value is approaching infinity and the y value is at the same time. And similarly, if I take the limit as x approaches positive infinity of f of x, this graph is going down, so I get negative infinity. Okay, so now I think so we're going to dig into a bunch of examples of these infinite limits here, but we're going to just take a slight detour backwards here and talk about connect this to ideas that you already know about from algebra. So you should notice when you look at this picture, what do these look like? Oh, these are horizontal asymptotes, right? So this is the real definition of a horizontal asymptote, is when the limit as x goes to infinity or negative infinity is a real valued number, that's a horizontal asymptote. So if as you go to the right, you approach a fixed y value, it's a horizontal asymptote. If you go to the left and it approaches a fixed y value, it's a horizontal asymptote. And with that in mind, when we go back and look at these graphs of limits that were going up to infinity, those are vertical asymptotes. So when we talk about a limit where the y value is going to infinity and the x value is going to a fixed number, those are vertical asymptotes. Anytime you get a y value approaching plus or minus infinity, that's what we mean when we say vertical asymptote. Okay, so now let's go back to our limits to infinity, right? What happens when x goes to plus or minus infinity? Okay, so we're going to look at a summary of some properties of limits at infinity. So these are pretty straightforward properties. The way we're going to use them is going to be to sort of rethink about these properties at each step in our problems. But, well, you'll see what I mean momentarily. So first of all, the limit as x approaches infinity of x to the nth power equals infinity. So this just says, hey, if I take a number and I send it to positive infinity, and then I raise it to a positive power, it's just going to be even bigger, right? 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, so forth and so on. So if I already have an input that's growing to infinity and I'm raising it to a positive power, yeah, that's just going to be even bigger. So that goes to infinity. If x goes to negative infinity and we have x to the n, well, then if n is even, you get positive infinity. If n is odd, you get negative infinity. So why is that the case? Why is that different? Well, let's take a look. So if I've got x going to negative infinity, let's look at negative 1 squared. That's 1. Then negative 2 squared. That's 4. Negative 3 squared. That's 9. So if I've got a square term here, or any even term, the negative is going to be canceled, and this thing's going to keep growing larger to positive infinity. But if I had, say, a cubed term, negative 1 to the 3rd power, that's negative 1. Negative 2 cubed is negative 8. Negative 2 to the 5th power, or that should be negative 3. Got mixed up there. Negative 3 to the 3rd power, that's going to be negative 27, right? So in this case, your outputs will always be negative values that are growing in magnitude, so we get negative infinity for any odd power there. Okay, so this next fact says, hey, if x is approaching positive infinity, so x is just positive values, and I have k times x to the n, well, it's infinity if k is positive, it's negative infinity if k is negative. That should make sense, because x to the n is going to positive infinity if x is going to infinity, and then I'm either multiplying it by a negative or positive number. If I'm multiplying it by a positive number, positive times positive is positive. If I'm multiplying it by a negative number, I get a negative times a positive. That's negative. All right, I'm not going to summarize this whole one, but it's the same logic here, right? Limit as x goes to negative infinity of k times x to the n. Basically, we got to check what's happening to this x to the n and what is k, and just check what our factors are, positive or negative. So when we're dealing with just polynomial expressions, this is really what we're going to use mostly, is these first 4 properties. But whenever we're dealing with rational expressions, these are going to be the ones we use. And these are really, I think, kind of the most important for our main, the main problems we're going to practice here. The limit as x goes to infinity of k over x to the n is 0, and the limit as x goes to negative infinity of k over x to the n is 0. So let's look at a simple example. I got 1 over x to the n. So if I look at 1 over 1, that's 1. If I look at 1 over 2, that's 1/2. I should say 1 over x squared. Let's actually pick a value. So 1 over 1 squared is 1. 1 over 2 squared, that's 1/4. 1 over 3 squared, that's 1/9, so forth and so on. If I have 1 over -1 squared, I still get 1. If I have 1 over -2 squared, I get 1/4. Now I might get negative values if I had an odd power here, but they would still be values that were getting closer to 0. So in any case, no matter what combination of a constant and x to the n that you have going on here, or power for n, as long as n is a positive integer, you're going to be approaching 0 with these kinds of fractions. So that's going to be a really useful tool for us, and we'll see how we use this to solve problems momentarily. All right, one more fact before we start doing these examples. Limits at infinity for polynomials. For any polynomial, p of x equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus blah, 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 plus a0. The limit of the polynomial when x goes to plus or minus infinity is the same as the limit of just the first term. Okay, that seems a little tricky, and how can we actually justify that? That should be the question. Well, it's pretty easy to justify by factoring out this a sub n times x to the n term. Okay, but it's sort of a weird factoring because what do we get? We've got to divide all of the other terms by this, right? So that's what you should be thinking of. If I'm factoring it out, it's like dividing all of the terms inside the parentheses by the thing that you pulled out. So we get an minus 1 over an times x, because this is xn minus 1 over x to the n, leaves me with one factor of x left. Oh, I forgot my 1. 1 plus. So when I factor it out of the first term, I get left with 1. And then I get a sub n minus 1 over a sub n times x plus blah, 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 plus a1 over a sub n times x to the n minus 1 power, because I've got x over x to the n, plus a naught divided by a n x to the n. The key thing here is that all of these are constants divided by powers of x. And what did we see in properties 5 and 6? These things all go to 0. So if these things all go to 0, then when I take the limit, then I'm just getting this times 1, right? So that's why we can just treat the limit of these polynomials as the limit of the highest power term. So I'll do a quick example here. A little side example. We'll do a more proper example momentarily. If I have the limit as x goes to infinity of, let's say, 3x squared plus 7x, what this says is, hey, I don't need to worry about the 7x if I'm taking x going to infinity. This only works for x going to plus or minus infinity. That's really important. Instead, I can just take a look at x going to infinity of 3x squared. The x squared goes to infinity. I'm multiplying by a positive number. The whole thing is going to positive infinity. Okay, so we'll put that on the back burner and we'll come back to the polynomial problems. Apparently I left out polynomial problems. Oops. How about we do one more little side example and then we'll go on to our regular examples. Bonus examples, we'll call these. The limit as x goes to negative infinity, let's say, of 7x cubed plus 5x squared plus 1. So again, this is a limit as x goes to plus or minus infinity of a polynomial. So I can just look at the first term, the highest powered term. That's important. You might get a homework problem where the terms are written out of order. You're always looking at the highest powered term. And now here, the x cubed, I'm taking something going to negative infinity. A negative cubed is negative. So this whole thing is approaching negative infinity, and this is approaching 7. A positive times a negative is a negative, so the result here is negative infinity. Okay, so that's how we deal with polynomials when we're taking limits to infinity. Now let's look at some rational functions. Now for rational functions, we want to use these two properties, 5 and 6. If I have a constant over x to a positive power, the limit as x goes to plus or minus infinity is 0. So what I'm always going to do for these types of problems, again, problems where x approaches plus or minus infinity, and you get a rational function here, I'm going to multiply the top and bottom by 1 over the highest power of the denominator. Now, technically speaking, you could choose to look at the numerator for your highest power, but in general, like this problem, it would work out the same because they both have the same highest power. But in general, it will make it more confusing to figure out your final evaluation. So you always want to use the highest power of the denominator, or bottom function here. So let's see what happens when I distribute this. I get 3x cubed over x cubed, that's 3, plus 5x squared over x cubed, that's 5 over x. And I multiply across the top, I get 4 plus 1 over x cubed times 3x. X over x cubed is 1 over x squared, plus 5 over x cubed. And what do we know from properties 5 and 6? All of these things go to 0. 3 over x squared, 5 over x cubed, 5 over x. A constant divided by x to a positive power. When x goes to plus or minus infinity, those go to 0. And so I just get left with 4/3. Okay, so why did we always multiply by the highest power of the denominator? Because it ensures that my highest powered term becomes a constant. And if I have just a constant in the denominator, then things are much simpler to evaluate, as we'll see in the next couple of examples. So for this next example, example 6, we're going to do the same exact approach here. Got the limit as x goes to negative infinity of 4x cubed plus 3x plus 5 over 3x cubed plus 5x squared. And it's the same function, but here we're just looking at the limit as x goes to negative infinity, and we're still multiplying by 1 over x cubed. And again, all of these terms still go to 0. Remember, that fact that we're using 5 and 6 here, they don't care if x goes to positive infinity or negative infinity. You're still going to get 0 for a constant over x to the power, to a positive power. So this is still 4/3. We get the same thing for that limit. All right, now let's look at an example that's a little bit more different. So this is the limit as x goes to infinity of 5x to the 7th plus 5x cubed plus 71 over 4x squared plus 3x plus 2. So I'm going to take the same exact approach here, and I'm going to start, and I'll just write it here, by multiplying the top and bottom by 1 over x squared. Again, the highest power of the denominator, always. Many times I'll see students try to use the highest power of the numerator and get stuck when they try to evaluate it, because it becomes much harder to analyze. So just stick with the highest power of the denominator. When I multiply this out, 4x squared over x squared is 4, plus 3x over x squared, that's 3 over x, plus 2 over x squared. Again, look, we get left with a nice constant in the denominator. Now up top, we have 5x to the 7th times 1 over x squared. That's 5x to the 5th. Plus 5x cubed over x squared, that's plus 5x. plus 71 over x squared. All right, now let's analyze. 3 over x, that's going to go to 0. 2 over x squared, that's going to go to 0. 71 over x squared, that's going to go to 0. Now the denominator's left with just 4, but the numerator has these two terms which aren't fractions. These are both going to infinity, so this goes to infinity. So if my numerator is going to infinity, my denominator is going to a whole number, that means this fraction is growing unbounded to infinity. All right, let's move on. We'll do another example. So this time we're taking the limit as x goes to negative infinity, 3x cubed plus 6x squared plus 7x plus 2 over x to the 5th plus 4x plus 1. And again, I'm going to multiply the top and bottom by 1 over x to the 5th. That's my highest power of my denominator. When I distribute the denominator, x to the 5th times 1 over x to the 5th is 1, plus 4x over x to the 5th, that's 4 over x to the 4th, plus 1 over x to the 5th. And my numerator, 3x cubed over x to the 5th, that's 3 over x squared, plus 6x squared over x to the 5th, that's 6 over x cubed, plus 7x over x to the 5th, that's 7 over x to the 4th, plus 2 over x to the 5th. And again, we look at all of these terms I'm circling. Constants over x to a positive power. Our limit is x goes to negative infinity, so these things all go to 0. So up top, what do I get left with? I get left with 0 divided by 1, which is just 0. Okay, so that's it for that example, and now we got one more here. Well, two more, I should say, even though they're both labeled example 9. That second one should be labeled example 10. Let's just go ahead and fix that. All right. An online seller estimates that their workers can package P of X equal to 30 plus 25X over X plus 1 packages per day after X days of training. How many packages does the seller expect a worker to package per day in the long run? Well, that just means take the limit, right? Take the limit as the number of days goes to infinity. That's what we mean when we say something generic like in the long run when we're referring to the behavior of a function. Oh, well, how do I do this? Well, this is a polynomial divided by a polynomial, so I'll multiply by 1 over the highest power of the denominator, just like before. So this is the same as any of our other problems. That's 30 plus 25 divided by 1 plus 1 over x. 1 over x goes to 0. And so this is just 30 plus 25, which is 55. Okay, now that that's out of the way, let's wrap this up by taking a look at a graph. So use the graph to determine the limit as x goes to infinity. All right, well, let's start with that one. So I find my graph, I trace towards the right, x is going to infinity towards the right. What's the y value approaching? Oh, 0. So this limit is 0. Now the limit as x goes to negative infinity. I find my graph, I trace towards the left. What y value am I approaching? Oh, this y value is 1, negative 1, I should say. So this limit is negative 1. And now we look at the limit as x approaches 2 from the left. So where's 2? That's here. So if I find my graph and I go towards 2 from the left, my graph is going down. So this limit is negative infinity. And if I go to 2 and I go from the right, my graph is going up. So that's positive infinity. All right. Well, that's it for this one. Thank you for watching. Have a great day.